We've talked about how to add vectors graphically, but a lot of the times we want to be able to use our calculator and to calculate these more precisely. So whenever we're doing vector mathematics in real life, what our process is going to be is to, number one, break all of the vectors up into their components. Instead of having one, two, or three-dimensional problem, you're going to have two or three one-dimensional problems. Once you have your components, you're going to do all of your algebra, all of your calculations as usual by component, by direction, for how many dimensions of motion you have. Once you've completed all those calculations, you can recombine the components to find the magnitude and direction of the overall vector. So one three-dimensional vector becomes three one-dimensional calculations, and we know how to do these one-dimensional calculations. An example of this is vector addition and vector subtraction. We've talked about how to do vector addition or subtraction using the tip-to-tail method. You see that here, where vector A is being added to vector B, and together the two of those are giving us vector C here. And notice as well that when we break these up into components, we have the x and y components of vector A, we have the x and y components of vector B, and notice here that the x component of vector A plus the x component of vector B gives us the x component of vector C. Likewise, the y component of vector A plus the y component of vector B gives us the y component of vector C. So when we're adding these vectors together, really we can add them. If we're adding them as vectors, we can add them by components. Adding the x components gives us the x component of the resultant. Adding the y components gives us the y component of the resultant, and so forth. We've also talked about how subtraction is the same as addition. Instead of adding a value, we're adding instead of subtracting a value, we are adding a negative. And the same way, if we're subtracting a vector, we can subtract all of the components one by one. Furthermore, we can multiply a vector by a scalar using the same idea. If we have a vector here, we can multiply this vector by a scalar. Notice that here I have vector A, and here I have vector B, where vector B is 2 times vector A. And so for vector B to be 2 times vector A, what that means is that we have to have the same direction. When you multiply by a scalar, you don't change the direction, so you don't change the angle here. If you multiply by a scalar, that scalar multiplies the magnitude. So vector B has a magnitude that's twice as long as vector A. But this goes straight back to regular trigonometry. If you have the same angle in a right triangle, then these two triangles are considered to be similar triangles. And it means that all of their sides are proportional. If the hypotenuses are twice as long, all the sides should be twice as long as well, because the trigonometric functions of that angle should be the same. And so if we multiply our vector by a scalar, we can multiply each component by the scalar as well.